Course Introduction. Welcome, I'm happy to teach the fundamentals of functional reactive programming with Rxjs and Typescript. In this course, we are tackling the fundamental concepts of Rxjs typed with TypeScript. We will learn how functional programming is enhanced with reactive programming concepts. You're supposed to be an intermediate JavaScript programmer with interest in functional programming concepts. If you have experience with JavaScript array methods like map or reduce, you are well equipped for this course. Let's look at the agenda of this course. 1. Origin and evolution of Rxjs. 2. Rxjs community. 3. Functional reactive programming. 4. Rxjs observable is a monad. 5. Iterator and subject observer pattern. 6. Mathematical dual. 7. Rxjs core components. 8. Operators, a higher order functions. 9. Strong typing with TypeScript. 10. Operator categories. 11. Create custom operators. 12. Error handling. 13. Multicasting with subjects. 14. Schedulers and concurrency. 15. Operator behavior visualization. 16. Integration with web frameworks. 17. Rxjs best practices. 18. Writing a business domain DSL in Rxjs. 19. Advanced architecture styles. 20. Conclusions and Rxjs future. The goal of this course is to understand the underlying concepts of Rxjs, functional programming, reactive programming, functional reactive programming, programming with monads, functional programming, pure functions, functions that always produce the same output for the same input and have no side effects, not modifying external state. They are predictable and easier to reason about. Immutability. Data is immutable, meaning it cannot be changed once created. Instead of modifying data, functional programming creates new data structures, which helps avoid unintended side effects. First-class and higher-order functions. Functions are treated as first-class citizens, meaning they can be assigned to variables, passed as arguments, or returned from other functions. Higher-order functions take functions as arguments or return them, declarative style. Focuses on what to compute rather than how to compute it as it is done in imperative programming. Code describes the desired outcome using expressions, often avoiding explicit loops and control flow. Referential transparency. An expression can be replaced with its value without changing the program's behavior. This property, tied to pure functions, simplifies reasoning and optimization. Avoiding side effects, functional programming minimizes side effects like mutating global state or running I/O, making code more modular and predictable. Recursion over loops. Recursion is often used instead of iterative loops for control flow, as it aligns with immutability and functional purity. Tail recursion is commonly optimized in functional languages. Lazy evaluation. Expressions are evaluated only when the results are needed, which can improve performance and enable infinite data structures. Reactive programming is a paradigm focused on building systems that are responsive, resilient, and scalable by handling asynchronous data streams and events. Its essential characteristics include asynchronous data streams. Reactive programming centers on processing streams of data like events, messages, or updates asynchronously, allowing systems to handle data as it arrives without blocking operations. Event-driven. Systems react to events like user inputs, sensor data, or network messages rather than relying on sequential or imperative control flow, enabling responsiveness to real-time changes, data flow, and propagation of change. When data changes, updates propagate automatically through the system. This is often achieved using observables or streams, where components subscribe to data sources and react to new values. Non-blocking. Operations avoid blocking threads, using techniques like callbacks, promises, or async await to handle I/O-bound tasks efficiently, improving scalability and performance. Back pressure. mechanisms to handle scenarios where data production outpaces consumption, ensuring systems remain stable under load by slowing down producers or buffering data. Immutability and functional principles. Reactive programming often leverages immutability and pure functions borrowed from functional programming to ensure predictable transformations of data streams and avoid side effects. Resilience and fault tolerance. Systems are designed to handle failures gracefully, often using techniques like retries, timeouts, or fallbacks to maintain responsiveness under errors or high load. Declarative style. Code focuses on defining what should happen in response to events or data changes, rather than how to manage control flow, making it more concise and easier to reason about. Functional Reactive Programming, FRP, combines principles of functional programming and reactive programming to create systems that handle asynchronous data streams in a declarative, composable, and predictable manner. Below are the essential characteristics of FRP: pure functions and immutability. FRP relies on pure functions where the same input always produces the same output, no side effects, and immutable data structures, ensuring predictable transformations of data streams and avoiding unintended state changes. Asynchronous data streams, FRP models time-varying values like sensor data as continuous and UI events as discrete streams. Declarative event handling. Instead of imperatively managing how events are processed, FRP allows developers to describe what should happen when events occur using high-level, composable operations like map, filter, or fold on streams. Composability. Streams and signals can be combined, transformed, or composed using functional operators, e.g. map, flat map, merge, enabling modular and reusable code for handling complex event-driven logic. Time as a first-class concept. FRP explicitly models time, treating values as functions of time or sequences of events over time, allowing precise reasoning about dynamic behavior. No side effects. By adhering to functional programming principles, FRP avoids side effects in event handling, making systems easier to test, reason about, and maintain. Referential transparency. Operations on streams are referentially transparent, meaning they can be replaced with their results without altering program behavior, enhancing predictability and optimization. Backpressure and resource management. FRP systems often include mechanisms to handle backpressure, managing fast data producers versus slow consumers, and optimize resource usage, ensuring scalability and responsiveness. Event propagation and dependency tracking. Changes in one stream automatically propagate to dependent streams, maintaining consistency in a declarative way, similar to reactive programming's data flow model. FRP is particularly effective for building responsive, event-driven applications like user interfaces, real-time systems, or animations. It is implemented in libraries like Rxjs, RxJava, Elm, blending the robustness of functional programming with the flexibility of reactive systems.